So in the last session, we have been talking about symmetric group, the group of permutations on n objects. Today, what we are going to do is we are going to study the structure of a permutation on n objects. So let us start with the symmetric group. Let Sn be the symmetric group of permutations on n elements, and sigma belongs to Sn. It's a permutation. Now we want to study the structure of this permutation. So this sigma is defined on n elements. So let's A is equal to 1 to n. So sigma is defined on this finite set. Now, with respect to that, the permutation, we are going to define a relation in A. How do you define a relation in A? Take two elements, A comma B, in A, and define a condition says that A is related to B if that condition holds good. So the condition here is for A, B in A, define sigma, the tilde, this is the relation, and this is based on the particular sigma. If you want, you can write it as sigma like this. So we are going to define a relation on A based on that particular sigma. Define sigma as A is related to B. I'm going to skip here because I'm going to assume that it is going to be based on that permutation sigma. If A is equal to sigma to the power of k of B for some integer k. Now our claim is the relation is an equivalence relation. And that means it is reflexive, it is symmetric, and it is transitive. Reflexive means A is related to A for all A in A. This is because A is equal to sigma 0 of A. And sigma 0 is the identity map, identity permutation. Symmetric means A is related to B implies B is related to A. And because A is related to B implies A is equal to sigma to the power of k of B for some k. And that implies B is equal to sigma to the power of minus k of A. Take the inverse of sigma. For every sigma in Sn, there is an inverse. So that means it is symmetric. So this implies B is related to A. So the relation is reflexive and symmetric. And it's also transitive because A is related to B and B is related to C implies A is equal to sigma to the power of k1 of B and B is equal to sigma K2 of C. And that implies A is equal to sigma of K1 K2 of C. And that implies A is related to C. So why are we doing this? Because an equivalence relation divides an equivalence relation on a set divides the set into disjoint subsets called classes. So this this tilde, the relation tilde divides A into disjoint subsets or classes called, in this case it's called orbits. I'm going to give you an example so that this relation is very clear. So we are going to assume that n is equal to 8. We are going to take a permutation on S8. So n belongs to S8 defined by sigma is equal to 1, 2, 3, 4, 5, 6, 7, 8. 3, 6, 1, 8, 2. This is 5. This is 7, 4. So you have all the elements here 1, 2, 3, 4, 5, 6, 7, 8. So this is definitely a permutation in S8. Now we'll see sigma of 1 is equal to 3. That implies 3 is related to 1 or 1 is related to 3. So sigma of 3 is equal to 6, and that is actually equal to sigma square of 1. So that implies 1 is related to 3 is related to 6. And sigma 6 is actually equal to 1, so they are closing it. So we don't have more than 3 elements in this class. So that is actually 1 to 3 and 3 to 6 and 6 to 1 and comes back here. So that is an orbit. So that orbit is actually 1, 3, 6. Take another orbit. Let's say sigma 2 is equal to 8 and sigma 8 is equal to 2. So that means this orbit is 2 and 8. So this is like this. See? Then it goes all the way here and comes back here. The next one is going to be, so this is another, the next one is going to be 4, 7 and 7, 4. 4, 7 and 7, 4. And the third is going to be just 5. So 1, 2, 3, 4, 5, 6, 7, 8. So the A right now we have is 1 to 8. So this is actually divided into 3 disjoint subsets. 1, 3, 6, 2, 8, 4, 7, and 5. So these are the orbits of. So how do you define the orbit? An orbit of a permutation sigma is the disjoint class of a relation tilde defined by A is related to B if A is equal to sigma k of B. So this is the definition of an orbit. So let us take the same example again. Sigma belongs to S8 defined by 1, 2, 3, 4, 5, 6, 7, 8, 3, 6, 1, 2, 8, 4, 7, and 5. So the orbits of sigma are 1, 3, 6, 2, 8, 4, 7, and 5. These are just orbits are just the subset of the base set of n elements. Okay. Now, if you take this orbit 1, 3, 6, we can create a permutation using this 1, 3, 6 in S8 by fixing the all other elements in the base set as it is and rotate 1, 3, and 6. What I mean is, this is actually corresponds to a permutation 1, 2, 3, 4, 5, 6, 7, 8, where 1, 3, and 6 are just like here, 3, 6, 1. But I am not changing 2, 4, 5, 7, and 8. So this is another permutation in S8. The property of this permutation is that its orbits are 1, 3, 6 as it is before, and the other orbits are all singleton, 2, 4, 5, 7, and 8. Because except these three elements, none of the other elements are moved by this permutation. This permutation is different from sigma. This permutation is created from one of the orbit. This type of permutation is called a cycle. So the definition of a cycle is a cycle is a permutation having at most one orbit having more than one element. meaning only one orbit of this permutation should have more than one element. Maximum. If all the orbits are of one element, then that becomes the identity permutation on Sn. And that is also a cycle. Now, this will also, you can write this also as another cycle. So that is actually 1 dash dash 8. I am not going to write everything. 2 is going to be 8 and 8 is going to 2. All others are same. 1, 3, etc. So each of these orbits can be rewritten as cycles. Now, we are going to prove this, but I'm going to verify this first so that we have a good understanding when we are proving the theorem. See, if you take this permutation 1, 2, 3, 4, 5, 6, 7, 8, 1, 3, 3, 6, 1, 2, 8, 4, 7, and 5. What I'm going to do is, I'm going to write the permutation corresponding to each of the orbits. Corresponding to each of the orbits. So this is actually 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There are actually 1, 2, 3, 4 orbits, and I am going to create 4 permutations. The first permutation is the permutation corresponding to the first orbit. This is 3, this is 6, this is 1. And all others are same. So this is different from here, but this is a cycle. Here, this is actually 2 and 8. 8, 2, all others are same. Next is 4 and 7. 4 and 7. And all others are here. There's only one element and that is fixed, so this is going to be an identity map. Now, all these are cycles. This is not a cycle because this has got more than one orbits having more than one element. Here, all the permutations are cycles because they have only a maximum of one orbit having more than one element. Now, if you compute this, how do you compute? You start from here, go here, go here, and go here, and things like that. So, this will be 1, 2, 3, 4, 5, 6, 7, 8. So you start from here 1, 1, 1, 1, 1, 1, 1, 3. So this is actually 3. 2, 2, 2, 2, 2, 2, 8 and 8, 8. So this is 8. 3, 3, 3, 3, 3, 3, 3, 6. 4, 4, 4, 7, 7, 7, 7, 7. So this is 7. 5, 5, 5, 5, 5, 5, 5, 5, 5, 5. So this is 5. 6, 6, 6, 6, 6, 6, 6, 6 and 6, 1. And 7, 7, 7, 4, 4, 4, 4, 4. So 7, 4. 8, 8, 8, 2, 2, 2. So 2. So you are getting the old permutation. So what is the result here? Any permutation can be expressed as a product of disjoint cycles. These are all disjoint cycles because an element is moved only in one permutation here. That is what this means. So if you take a 1 is moved only here. Here 1 is 1, 1 is 1, 1 is 1. So the result is any permutation can be expressed as a product of disjoint cycles. This is an example and we are going to give you a proof. So the theorem is this. Let sigma be any permutation in Sn. Then sigma can be expressed as disjoint cycles. Can be expressed as a product of this, can be expressed as a product of disjoint cycles. So we start with the orbits. So let B1 comma dash dash BK be the orbits of sigma. What I'm trying to say here is see the sigma which we took earlier on S8, 136 2 4 5 2 8 4 7. So these are the orbits of our 1 2 3 4 5 6 7 8 3 6 1 4 2 8 4 7 and 5. So these are the orbits of this sigma. So this is my B1, this is my B2, this is my B3 and this is my B4. So that is what I am trying to say here. So B1 to Bk are the orbits of. Then define mu1 is equal to sigma of A if A belongs to B1 or A if A does not belongs to B1. Let us take Mi. For example, here mu1 is going to be mu1 of A, sorry, mu I of A is equal to. So mu1 of A is equal to sigma of A if A belongs to B1. Otherwise, it is just A if A does not belong to B1. What it means is, if it's 1, this is 1, this is actually B1. So this will be, mu will be defined by, mu1 will be, if mu1 is a permutation defined by 1, 2, 3, 4, 5, 6, 7, 8, 3, 6, 1, 2, 4, 5, 7, the first cycle we considered. See, if A is in B1, that means if it is 1, then it goes to sigma of A, sigma of 1. Sigma of 1 is 3. So if you define like this, mu i's are cycles and sigma can be written as mu1, mu2 dash dash mu k. And that's what we want to prove. Because if you look at the definition of this map, an element in the base set will be moved only by one of the mu i's. This is because an element in 1 to n is moved by at most one of mu i's. At most, in the sense that in case if it is a singleton, it won't even move. For example, here 5 is not going to be moved by any of these mu's. So that is a proof of this. And one more trivial result from here is disjoint cycles commute each other. Meaning these are commutative. Not all the sigmas are commutative, but disjoint cycles are commutative. Meaning mu1, mu2 is equal to mu2, mu1. And that is how we defined it. Because if it is in A only, it is moved. Otherwise, it is not moved by that. Now we have a special cycle. A cycle with two elements are called transpositions. In here, where we get the sigma, 1, 3, 6, 2, 8, 4, 7, and 5. By the way, the cycles, I forgot to tell you about that in the previous, when we define cycle. A cycle is a permutation with at most one orbit having more than one element. So here 136 is a cycle. So this is actually a permutation. Even though I wrote only 3 elements here, all other elements are fixed. So a cycle can be written like this. A cycle can be written as a permutation with only the elements that are moved. So this is actually 1, 2, 3, 4, 5, 6, 7, 8. 3, 2, 6, 4, 5, 1, 7, 8. This is actually this permutation. But you don't need to write the whole thing. You can write it as 136 notation. So I just want to make sure that you are not confused with this. This is actually a permutation corresponding to the orbit with the 1, 3 and 6. So, I'm sorry, again, sigma is equal to 136, then 2, 8, then 4, 7, then 5. A cycle with maximum a cycle with 2 elements are called transpositions. So these are transpositions. Transposition. By the way, 136 and 361 and 613, these are all same. You can write it in either way. You can rotate the elements. This is actually a transposition because it contains only 2 elements. So the way we are going to compute when you write it like this, so what you will do is you write 1, 2, 3, 4, 5, 6, 7, 8. Then you compute from here, or you can compute from here. These are all disjoint cycles. So it is commutative. You can start from here or you can start from here. Let us start from the right side. 5 goes to 5. There is no 5s that are moved here. 7 goes to 4, and 4 does not move anywhere before this. So 7 goes to 4 and 4 goes to 7 because it is not moved anywhere here. So like that, 8 goes to 2 and 2 goes to 8. Like that, 3, 6. That is how you multiply the disjoint cycles. Now, when the cycles are not disjoint, then we need to compute from the right side and go to the left and taking care of all the duplicates. For example, let us assume that you have a cycle here. A1, A2, A3, AN. Okay? Now I'm going to let us take another simple example before we come here. Let us take a simple example. Let's take a sigma in S3 defined by sigma is equal to 1, 2, 3, 3, 1, 2. So this is actually written as 3, 1, 2. This is how it's written. No, not like that. This will be written as 1, 3, 2. 1 goes to 3, 3 goes to 2, and 2 goes to 1. Now, this permutation, I'm going to write it as a product of two transpositions, like 1, 3 times 1, 2. These are not disjoint cycles because 1 is appearing in here. Okay? What does this mean? This means that 1, 2, 3, 1 goes to 2, 2 goes to 1, and 3 is same. Here this means 1, 2, 3, 1 goes to 3, 2 goes to 2, and 3 goes to 1. Now you multiply. Take the product. So 1 goes to 2, 2 goes to 2. I'm sorry, I'm going to take product of 1, 2, 3. If this is 1, 3, 2, I'm going to take 1, 3, 2. So this is going to be 1, 2, 3, and this is going to be 1, 3. Okay, so we start from here. 1, 3 and 3, 3. 2, 2, 2, 1. 3, 1, 1, 2. And that is exactly what we are coming from. So if you write, this is our 1, 3, 2. And I am going to write it as 1, 2, comma 1, 3. So similarly, this can also be written as A1, AN, A1, AN minus 1, dash dash, A1, A2. And if you compute this one, you are going to arrive at here. So this is just a computational exercise. I'm not going to prove this one because if you expand this one, 1 goes to 2, A1 goes to A2, and A2 is not moved anywhere here. So A1 goes to A2. Now A2 goes to A1. That A1 is going to A3. So A2 goes to A3. And the previous one, this will be A1, A4. So it will be A3 is going to go to A4. Things like that. So what we can write is any cycle can be returned as a product of transpositions. These are not necessarily disjoint. Actually, these are not disjoint at all because A1 comes in every single transpositions. Any cycle can be written as a product of transposition, and that implies any permutation can be written as a product of transposition. This is a cycle and this is a permutation, but we know that every permutation can be written as a product of disjoint cycles, and each cycle can be written as a product of transposition. So every permutation can be written as a product of transpositions. Let us do a problem. Express the following permutation in S8 as a product of transpositions. Sigma equal to sigma equal to 1, 2, 3, 4, 5, 6, 7, 8, 1, 8, then 3, 6, 4, 3, 6, 4, and 5, 7. 5, 7. So this can be written as, we are not considering this 2 because that is not moved at all. So this can be written as 1, 8, 3, 6, 4, and 5, 7. 2 is not moved anywhere, so we don't need to write it. So this is this I expressed first is expressed as a product of disjoint cycles. Out of these cycles, these two are already transpositions. So we need to convert only this cycle as a product of transpositions. So this will be 1, 8, and this will be 5, 7, and this will be 3, 4, and 3, 6. So this is the product of 4 transpositions. So we are expressing this sigma as a product of transpositions.